Are you a business owner looking for real advice and input? You're in the right place. From concept to launch to growth, funding, and beyond. Welcome to Startup Hustle with your hosts. One once sold a business for $150 million. The other, the author of $1 Million Bedroom. Here are your hosts of Startup Hustle, Matt DeCoursey and Matt Watson.
And we're back. Another episode of Startup Hustle. Matt DeCoursey here with Matt Watson. Hi, Matt.
What's up?
I'm just kind of getting through another day here. I'm, trying something new, going headphone free.
Yeah.
Commando.
Yeah.
Commando.
Yeah, I am kind of rolling commando. Anyway, before we get started, I want to let everyone know this episode of Startup Hustle is brought to you by Fullscale.io. You can also check out the video feed of today's show on our YouTube channel. So with us today, we have Todd Gentry and Patrick Hosty from HyperBorean. Hi, guys.
Hey.
Hello.
Well, first off, thanks for coming in, and I'm looking forward to you guys attempting to explain to me and us the amazing clean tech products that you're trying to build. But just so we can get a little bit of identification here. Mr. Gentry, you are an inventor and the CEO of the company. Is this true?
This is true, and founder.
Okay. And Patrick, you just said you're number two.
I am number two.
And we appreciate that. So the world of invention is challenging, and obviously something that a lot of people have a lot of great ideas. I think we should go ahead and start with maybe Todd or whoever wants to take it, talking about the invention process and what you guys are trying to accomplish with HyperBorean.
So this all got kicked off about 4 years ago with a group from UT Austin doing a lot of the heavy lifting. So the invention process for us has been kind of in phases. We started with cocktail napkins and then spreadsheets and then finally computer modeling, and it got to the stage where they said, here's our best effort. We're going to hand this over, and it's now up to you to build this. So that's been the most exciting phase for me. Shepherding the cats through the process for 4 years was interesting and challenging, and helping them iterate and ideate for the solutions that we were looking for was good. But the hands-on part has really been cool, and we're emerging from the initial prototyping efforts into testing and identifying the parts that need to be upgraded and improved upon as we get ready to roll into production.
So we step back for a second, though. How did you get started with this from the very beginning?
And what are we doing?
Yeah.
That's a really good spot.
What's the problem we're solving here?
So the problem we're solving is that air conditioning is a massive and ever-growing draw on the world's electricity supply. And that has not only production issues, but also environmental issues to it. And so we have taken an approach of using the most abundant source of energy on the planet, which is waste heat, to power air conditioning. So the goal is to essentially have off-grid free air conditioning, which runs off of something like concentrated solar or off of a car's engine heat. Other sources of heat that are available to us are also fair game. And the idea is to cut the global energy consumption that's used for cooling.
So how'd you come up with this idea, though? You were sitting on your back porch drinking a beer, and you're like, it's hot as shit out here.
He was off the grid.
And my AC bill is too high. Yeah. I got to solve this damn problem.
How did you off the grid? Like, man, I'm hot.
The porch with beer is actually accurate.
So this has been almost 2 decades in the making. Kind of my background is popped out of K-State as a degreed engineer, went right to work for a small town manufacturing firm that did burners for boilers. So our job there was to produce a lot of heat, learn how to control that heat, and harness that heat. So I got introduced right out of the gate to various sources of heat and the issues around it. As part of that job, they sent me all over the world before it was over to learn about different applications and ways that we could better do our jobs. And while I was at that company, a guy that was their IT person and I ended up co-founding an internet service provider business. We kept our day jobs for a while until the thing just went absolutely nuts. But as that business was growing, I became painfully aware of the need to keep the equipment that we used cool, not only inside controlled areas like buildings, but also in weird remote locations where we had to build equipment shelters and put stuff out in the field. And it was just astounding to me how much money we were spending on cooling and the challenges to keeping that equipment that provided the cooling operating in these weird, dusty environments. And so I married those two things together and thought there's got to be a better way. There's got to be a way to provide cooling for these locations and use all this heat that's out in the world that people aren't even totally aware of. And so that began it became the nexus of the idea of using waste heat to provide cooling.
So I have a question. So when you talk about like a remote equipment shed, all right, my uncle is a rancher, and they have, you know, these big ranches in Texas that are, I mean, they're not technically off the grid, but they are.
Yeah.
And so, you know, they use solar power as gate openers, you know, like, you know, just to open the gate, because there's no way you're running a wire out there. So theoretically, if there was an equipment shed somewhere on the ranch, what we're trying to do is reuse the heat that's already being generated to do something there in place of wiring up the actual unit, or is that to just, I mean, is that part of it, or is it more about repurposing the excess energy to not have such a need for electricity in these remote locations?
It's really to not have the need for electricity. All of the locations that we are first working with, which are related to the mobile telecom industry and the railroad industry, have grid power to them, and copious amounts of it to provide power for the operation of the radios, the crossing signals, and the other devices that are there. But the power that's consumed for the cooling is a significant part of the power draw at these facilities and a big part of their cost structure. And using concentrated solar as our heat source, we can provide daytime cooling for these structures just powered by heat, cut their grid demand, and then also add a lot of resiliency in the case of a grid failure, so that if these facilities have to switch over to battery power or generator power to operate in the event of a grid crash, that generator or battery is also providing air conditioning without our devices, and it depletes either of those options very quickly.
So how does this device work?
So basically, we have modeled off of what everybody else is using for air conditioning right now, which is called Vapour Compression. It's like the unit that you see sitting outside your house. There's a chunk that has a compressor in it and a condenser, and then inside the house there's another piece that's an evaporator, and it runs vapor through the system and through phase change provides cooling. We have built on that platform, but we have simply come up with a compressor that now runs off of heat instead of electricity. So we can plug into existing systems with our compressor, either as an add-on, so that if it's powered by concentrated solar, it does daytime supplemental cooling. If it's a standalone, it's doing all the work, but it's based off of what everybody else is using, and that was kind of done intentionally so that we can work into licensing agreements, so that we can easily adapt and integrate into other systems.
So how do you run a compressor then without electricity?
The basic idea is, again, phase change. What we're doing is using standard refrigerants, which is also by design so that we're easy.
But I mean, how do you, so there has to be something to power the compressor, right? So you have to turn this heat into some way to actually mechanically power a compressor, right?
Correct. So what we're doing is using these refrigerant gases, which come out of the backside of the system as a low pressure, low temperature vapor, and we put them in our we call it a burst compressor. Basically, it's the core of the compressor itself, which is under a lot of intense heat. It's got a solar thermal input to it, or the other sources of heat that can contribute to it we've already mentioned, but it changes these low temperature, low pressure vapors into superheated gas, which dramatically increases the pressure of these gases in a confined space. So all of a sudden you've got a lot of extra energy that's now available to you.
So that gas becomes the fuel?
The gas becomes the fuel.
Interesting.
We use it in two ways. The standard function of a compressor is to put high pressure gas into a condenser and then works its way through the rest of the system. We burst this high pressure gas into the condenser in a very short amount of time, and we shut off that burst and let it work its way through the system. There are another couple of chambers in our system which then we use to do other work to continue to move the refrigerant through there. So it's using the high pressure gas in a variety of ways as it's changing phase. From
So are there any moving parts in this system?
Very few. We've got some valves. There's no refrigerant oil, which is also something that all of the HVAC guys get very excited about. That's kind of a messy part of their job.
There's no Freon?
There is Freon.
Okay.
We use the same type of stuff that's currently out in the field.
Okay.
So this is something like this exists. This works.
Yeah, we've got a working model. It's in the process of being converted from kind of a Frankenstein prototype into more of a production model so that we can get our first 10 pilots in the field, but we're getting close. We've identified a few weak points in the early designs that we're working to engineer around, but once we've got those challenges overcome, we are ready to put it out in the field.
This is interesting. So how much heat does it need before it'll actually power the system and provide some meaningful refrigerant?
We need a lot.
Need a lot of heat.
We're talking 900 degrees of temperature input.
Okay.
Using concentrated solar, the way that we're collecting that is through a Fresnel lens.
Okay.
And if you go...
Wait, let's stop, because I don't think anybody listening knows what a Fresnel lens is. Like, is that a magnifying glass of sorts, or?
It really is.
Is that the layman's way to put it? Like,
it's a lighthouse lens.
Okay.
So you've got this little point of light inside the lighthouse globe, and the Fresnel lens magnifies it tremendously. We flip that around so that this huge source of light, which is
way over my head. Sorry.
the solar
Most
energy,
things are. Okay.
I know.
Except that hat.
it converts it down to a small point of light. So if you want to see something cool, go to YouTube, look up Fresnel lens penny,
Okay.
and it'll show you them just vaporizing pennies with these things. It turns into a little green cloud of smoke. So that's what we're
Interesting.
doing, but instead of a very small pinpoint of light, we're doing a dollar bill size of light on
See,
a reflector.
when we talk about this and the different applications for it, the first thing that came to me, the thing that requires like more air conditioning than any damn thing in the world that I know of, is data centers.
Right.
And servers are hot. And so that was the first thing that came to me, is like, I wonder if this could work for servers in a data
Well,
center.
that's how that was part of how you kind of came up with the idea, right? Just like you mentioned keeping equipment cool. That's where it started, right?
It really is. And to answer your question directly, since we've built on the Vapour Compression platform, we're limited to the size range that typically does. And it's the industry terms, but it's a half ton of cooling up to 5 tons of cooling. And so the data centers are typically so large, and they have so many servers that they operate off of hundreds of tons of cooling.
Yeah.
So we would either have to cascade a whole bunch of these together or have very small data centers. So our focal point right now is more on the very small equipment shelters that have mission critical cooling needs in remote locations, and those again are in mobile telecom, railroad.
Yeah.
The-
I mean, the little telecom things are basically little data centers.
And speaking of needing to cool things down, Patrick, you're gonna have to slow down here. So you're on fire over there.
You're
He's
definitely
just-
number 2 at this
Yeah,
point.
well, I'm like number 4 here. So Patrick, you were my first exposure to HyperBorean. You came in, we just talked about some stuff, and you had used the railroad model and talking. So railroads. Well, you want to explain kind of what you were explaining to me, like where this is kind of practically applied, and it had to do with the little the stations, like the machine, the control units that. Now keep in mind, there's moving parts in these things that potentially need to be triggered from wherever, and maintaining and keeping up on those things is a little bit of a challenge. Can we kind of recreate our first conversation with that?
Oh, totally. A lot of the railroad crossings have small equipment shelters so that they can monitor data up and down the railroad. And this was required through positive train control. This is legislation that required the train systems to be more accurate up and down the system. And
To literally help avoid train wrecks.
correct.
Right.
And I mean, and other things. I mean, the telecom industry uses these railroad crossings to, like, the local municipalities use them, and they have the same problem as the telecom industry with cooling that same equipment. And one of the things that we learned when we participated in an accelerator called the Clean Tech Open was the resiliency that we provide to the equipment is just as impactful as the energy that's being used. So in addition to us saving that shelter cost on their energy, what's a bigger impact to our environment is the keeping the existing equipment lasting longer, because when that equipment fails, which it normally does, they just take it off the building, throw it away, and install a new one. So what we've learned as part of our green footprint is to help those equipment shelters not throw away their equipment, but have it last longer.
So do they cool those today? Do they have little air conditioners today?
Yeah, there's a picture on our LinkedIn page that shows there's a telecommunications tower in Lawrence that I drove by, and they had 3 different huts, and on each hut had 4 air conditioners.
And you can find this on your website, and that's HyperBorean.com, right?
It's coldfromheat.com.
Coldfromheat.com. As you can see, I did my research. So.
Yeah. So you can replace all 4 of those AC units, or do you guys just become like a 5th like backup unit?
We would be the supplemental cooling for that shelter, so we would help those existing units last longer.
Okay.
And run less.
So if I'm going to buy this, is your product, affordable, or will it be very expensive, or similar to buying an AC unit, or?
Yeah, that's kind of the other advantage of building off the Vapour Compression platform that we have. We've created a compressor that runs off of heat, and so essentially that's the novel part of our system. Everything else is essentially off-the-shelf HVAC stuff.
Mm-hmm.
So we put in our particular component to that. Everything else is the same cost structure as the HVAC guys are currently operating on. So we're pretty cost competitive end of the day.
So is that, I'm just kind of curious, does that end up being like a couple $1,000s or $20,000 or $5,000?
So when you add the tracking solar component of it, we're looking between $7,000 and $8,000 for a installed cost.
Okay.
So we've had guests on here before that are in the hardware business. Davion Ross at Shot Tracker was one that comes to mind, and Davion will say they call it hardware for a reason. What are some of the things that have been really hard with the development process? What are some of the real obstacles? Now, first off, clearly turning heat and Fresnel lenses and stuff like that. Wow, way over my head. But what were some of the biggest challenges that you've had to overcome building this, and what are some of the hurdles you still have to climb over?
So hardware is hard, and it is challenging also in that as you test and you find areas that need to be improved upon, the cycle to iterate, the cycle to recompile, if you're talking in software terms, is days, weeks, months at times based on fabrication times and re-engineering times that are needed. So part of it is just the timeline that's required to make changes. So
that's why 3D printers are a big deal.
Yeah,
they really are. And we've used a lot of 3D printing in our prototyping efforts. There's some of it because it's such intense heat, such intense pressures that we've had to go with ASME coated welding and very specialized manufacturing techniques. And so those sorts of things are some of the biggest challenges, is just the timeline to make improvements and figure out issues as they crop up. And then the rest of it is just the weird interactions that you start to see as you really marry the things up. It becomes an issue where you fix one problem and a new one's identified, and so then you're back to the whole iteration problem. So it's been a very long slog, and I think that's been one of the greatest challenges, is just managing the timeline and the expectations of, why isn't this on the market yet? What's the next step to get this ready? How can you move faster? And those are the things that we fight on a daily basis, and in very long days, is fixing problems and refining the design as quickly as you can. And
so what is the next step? You guys have this out in the field and some trials at this point, or kind of where are you guys at with that? We're
still in lab testing. We've got one more technical hurdle to overcome. It's become kind of we're zeroing in on it. It's become the final challenge to miniaturizing this, getting the cost wrung out of it. So our objective is to have all of the production engineering wrapped up by the end of 2019 and deploy the first pilots in Q1 of 2020.
And will that be at these train stations, or where will your pilots be?
Mobile telecom and railroad are our first stops, for sure.
So a little bit of a shout out here. A lot of people comment on the Startup Hustle sign we have here in the studio, and that was provided by a local metal fabrication shop called Wilclair. And they do a lot of the stuff like you were talking about. So this was a plasma cut. It was a giant piece of metal, but part of what they do is work with companies like yours. It's largely like manufacturing stuff. So that whole like ability to create these precision pieces. And when I was out there picking up the sign and talking to them about it, like, and with what you're doing, like a millimeter is like a huge amount of space. Sometimes like a millimeter could be like a mile. And talking about that just little precision stuff and how difficult it is to iterate all these moving parts and making them, especially when you only need 3, and and you can't, and you don't, at that point you don't have a metal foundry, and like, I mean, that's kind of the stuff you're talking about. And like at Wilclair, their major people that they deal with are like people that make large, like pharmaceuticals. So like in the pharmaceutical bin and all that stuff, like if they find one speck of mold in there, they might have to throw out everything.
We've been very lucky partnering with makerspaces. So here in Kansas City, we're a member at Hammerspace, and in Wichita, we are members at the Go Create facility, and have been able to cut costs literally.
So you challenge them with the different parts and things that you need, and that's a good practical application for them to dive into.
Well, for us to go to a Wilclair, like, I would think they would want multiple different iterations and the ability to fabricate at scale. At this stage of our startup, we need to be able to do one-offs and fail fast.
Yeah.
And doing that in a makerspace is a lot more economical at this stage for our startup before we're able to level up with.
So if you're doing it in this makerspace, do you guys have to do all the work, or are there people there that's sort of their hobby and they're helping do this stuff, or?
So the Go Create facility in particular is wonderfully staffed with mentors.
Okay.
And they stand over your shoulder and they say, kid, you're going to do that wrong. And then they guide you into
and you guys are figuring out how to fabricate metal pieces?
Yes, we're very much machinists at this point, which is, it's been fascinating and then also really beneficial, because as things do fail, as things break and need to be iterated, I've been the guy that built them. And
you understand how it works.
Yeah, and when I see...
Somebody's got to understand it.
When I see that the tolerances that I didn't quite hold have now shredded our rolling diaphragm, it's like, oh, that's why it had to be exactly this tolerance and this size, and so we'll go back and fabricate a new one. And
I mean, that's going to be the other thing is you guys will, 6 months from now, you'll have all this figured out, and you'll put these out in the field, and then they'll sit there for like 3 years, and you'll go back and be like, oh, these parts failed because of X, Y, Z. It's going to be the same stuff, right? Like that's the hard part about this hardware is then it gets out in the field and out in the wild. And
so we're always mentioning like riches and niches and stuff like that. And like the last thing we have to say about the metal fab shop, but like the guy that runs that is considered to be one of the foremost experts in like modern metallurgy. Like how many people do you know that are like, he's like a professor. And that's the kind of stuff that planning tries to take into consideration is like, well, how is this going to hold up?
Yeah.
And how is this going to react to so you can build a container or a piece or a unit, but what's going to happen when you put other kinds of chemicals on it? And just like, I mean, who knows?
In extreme heat, cold.
Extreme heat, motion, friction, just like over time. And then
corrosion.
Also when you're connecting pieces of metal to other metal, like this is something we ran into a lot when I worked for Roland. Just musical equipment. It's like just goofy things like solder joints. Yeah. Like you think about something being on a truck and it's like going in and bouncing, and like over time just these connections break. That vibration it ruins joints and stuff like that, and you just need one connection to fail before the whole rest of the thing comes up. All right, so Todd, I have found that whenever I meet an inventor, that they have invented a whole lot of different things, and they have done that. Like my guess is that from a young age, you were probably building stuff.
Always.
Okay, so let's take a alternate path here. What are some other things that you've invented, or maybe even what are some things you've tried to invent it and gone, I don't think so.
The way that passion kind of took shape was rolling out of the internet service provider business that we first started in '95. So this was the height of the dot-com days. We rolled out 28.8K modems as our first deployment.
I still use one.
We upgraded to 56K, and we had a a great exit in '97. Worked for the acquiring company until 2001. The acquiring company ran out of cash. They sold to Earthlink. We worked for Earthlink. When I was finally released from all of that, I said, I want to get back to creating. I'd kind of come out of the engineering world with the burner for boiler companies, and had jumped into the tech communications world with both feet. But as I emerged from that, I had some time, some capital, and I thought, what can I do that's really cool that I've always wanted to do? And I created a consumer products company. And one of our very first offerings was heated sports seats. So we used iron oxide packs. We could heat up seats to about 140 degrees, last for 12 hours. Amazingly fortunate to land in Walmart, Dick's Sporting Goods, right out of the gate almost. So this company kind of took on a life of its own, and it became the platform for throwing the spaghetti against the wall and seeing what would stick. So we have files of these various concepts that we've tried that failed miserably for a variety of reasons, and a couple that really stuck and took off great. But one of our biggest successes was a product that we didn't even conceive of, but repackaged, rebranded, and it became our top seller, and it was something called Firewire. It was a stainless steel flexible grilling skewer. So if you can imagine something that looks like a fish stringer, you load your meat, your veggies up on that, you put the pointed end through the loop, and it becomes a little lasso, and all of a sudden you can flip your kebabs just with a twist of the wrist, and it solved a ton of problems of kebab cookers. The sticks you don't have a stick, so there's nothing to catch on fire. You pick up the sticks, try to turn it. Some things turn, some things don't. You can marinate.
Struggle's real.
Yeah, you can marinate right on the skewer. And these are real world, huge problems that we were solving with all this.
Thank you, Todd, for changing the world.
Yeah, but it took off remarkably well. And so that was the platform that I really had to.
And so do you still own those things today or license those? Or
We had an exit in 2013.
Okay.
Various items got sold off prior to that. So that it was my release of all that creative energy for about a decade and 3 years. And when I finally had the last exit of the last product, I thought, it's time to get back to this heated, heat-powered cooling concept again. And so that was really what allowed me to roll into this full time and devote all energy to that.
So the invention space is really interesting. I'm assuming you know who Ray Kurzweil is. Okay, so do you, Matt?
No.
Patrick, do you? Okay, he's a very well-known inventor. Now he also had a line of keyboards at one point. He grew up as the son of an orchestral director, but Kurzweil's become one of the spokespeople for like futurism, basically, and singularity and stuff like that. But yeah. I was fascinated with his work, and one of the things he was always talking about is, as an inventor, if you're not working on what you want to build in 10 years right now, you're behind.
Right.
Like, so you're using what is it called? What the technology curve?
Moore's law.
Yeah, Moore's law. So the best inventors then that are doing the most iterative, the greatest things you're thinking about what you're going to build in 10 years, knowing that you can't get it done now, but you're almost waiting for what will be more available later. Did any of that mentality and thought process and that approach, does that apply to you, and did any of that apply to what you guys are building? And check it out at coldfromheat.com.
A lot of the early challenges were that we didn't know what we didn't know about the thermodynamic processes that we were working to put together into multiple processes into a single platform. So it kind of feels like we're in part of the Moore's law process right now. It took so long to get the architecture that I sketched out into some kind of semblance of a cohesive thermodynamic model, and it began to speed up as the computer modeling kicked in, and then it sped up a lot more as we started creating the actual parts. And it feels like that general path is being followed now as we're iterating the final bits of the prototype design into production design. So yes, a lot of the challenges that we've faced had never really been faced before in a model that incorporates so many different thermodynamic cycles. And it's not that anything's particularly bleeding edge, it's just that there was a lot of challenges to mass flow and conservation of energy and the other bits of this that finally made it work. So the Moore's Law effect has kind of kicked in terms of our path towards commercialization.
Now that's is that every 12 months or every 18 months?
I think it was 18 months.
And that means that you double the strength and you half the cost.
Yes.
And that's held pretty true, but I mean that's pretty crazy though, because you get pretty exponential as you get.
Yeah, Moore's Law. Yeah. I think realistically in computers is kind of ended already, but
has it though? I mean, with AI and
maybe in servers and data centers, maybe a little bit. But what they've done now is they keep adding cores to the computers. Like a single processor is not really any faster. It adds more cores. So if you have work that can take advantage of multi-threading and multiple cores, it might be faster. But
so this was probably 5 years ago that I found interest in this, and the comparative example that Kurzweil used is so. Once again, back to 5 years ago, he said in 20 years, the computing power of an iPhone will be able to be put in something the size of a red blood cell, which is like plays into nanotechnology and stuff like that.
So what's fascinating, a lot of the upgrades in HVAC over the years has been focused on fan blades and motors and making those parts of the machine more efficient. What's brilliant, what Todd has done, is he's focused on the compressor, which is normally a part that has been untouched in 50 years. That technology is essentially the same. So as we're able to use more efficient motors and fan blades in our system, by upgrading the compressor, we're making it compliant with Moore's Law.
I mean, are your compressor designs relevant back to other HVAC systems? Like,
absolutely. Our initial business model is to manufacture and sell equipment in these small equipment shelter applications, to get the product in the field, get some runtime data, prove concept, gain revenue. But the long-term goal is to morph into a licensing entity so that our compressor becomes part of the offering for Bryant, Carrier, Train.
Okay.
So that it's...
You think you've truly built a better compressor even for them?
Well, it's a different power source, at least, for the compressor, so that it can seamlessly switch back and forth between grid power and heat input based on the availability of the heat, which is kind of the long-term goal.
So that means could you run an HVAC system off only natural gas and do cooling?
You can definitely run it off natural gas. It would kind of defeat, unless you've got another process that's using that natural gas. You wouldn't want to use natural gas just to provide the heat for the cooling, because
that'd be like emergency cooling.
Now you continue to as we continue to record episodes, your proficiency with just general mechanics and motors. We determined recently you are a qualified mechanic, right?
Yeah.
Yeah. I got some work I'd like you to do on my car.
No.
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 I think some of that's fascinating now. Recently, at Full Scale, we became involved with Launch KC, local business accelerator, and some of their clean tech cohorts we recently met with, and one of them was, I can't remember the name. We'll put a link in the bottom somewhere, but they were dealing with power grid management. And Matt, you're a big advocate of the electric car.
Yeah.
I am as well. But one of the things he pointed out was, electric cars actually draw a significant amount of energy. Mm-hmm. And so if all of a sudden we immediately all had electric cars, there are some strains on power grids.
That's why the electric company runs ads on the radio now, promoting electric cars. I don't know if you've ever.
Oh no, but
that.
Interesting.
Yeah,
no, I don't listen to the radio.
I
only listen to this podcast because I like to. It lets me feel like I'm always around you, Matt.
Can't get enough, huh?
People ask me a lot. They're like, "What podcast do you listen to?" I don't. Sometimes ours, but but these are the kind of struggles that create an energy efficient system. Like is that part of the thought process there?
Absolutely, and I think that's one of the things that we do bring to the table with the daytime supplemental cooling is that in the U.S. alone, there's $1 trillion worth of generation equipment that sits idle about half the time, and all of that stuff is in place just to handle peak loads, and those peak loads are almost exclusively driven off of cooling demands in the summer. So you've got the least efficient possible generation facilities that are kept idle, when those have to engage, everybody's rates reflect that increased cost, and the environment suffers because these are the plants they try to keep offline for a variety of reasons. So if we can mitigate that peak load by doing the cooling during the peak cooling demand periods off of concentrated solar, we've kind of helped in a lot of areas. We've cut the end users' costs, we've helped utilities manage better their generation infrastructure, and there's also significant environmental benefits to that as well by keeping these least efficient of all plants offline as much as possible.
We've become pretty well acquainted to always having electricity when we need it here now. And Full Scale has an office in the Philippines, and we actually have backup generators in the building that we're in and our office at Full Scale. But once you get outside of the IT parks and other places like that, and they use the term brownout.
I was there.
Yeah, I mean, it's just like
I went out to the countryside, and the whole south side of the island had no electricity for like the whole day. Like we were gonna have like a party and dinner, and we're like,
and
no,
then there's
not
no
today.
electricity. Yeah, and you don't know when it's like. And before we had an office years ago, when I only had remote employees, sometimes we'd like be in the middle of a meeting, we'd be talking on Skype, and all of a sudden it was just like black. Brown. You're like,
but a lot of those,
I know what happened. Brownout.
A lot of those generators that you mentioned, people don't put the gas powered in front of that.
Mm-hmm.
So it's many of the telecommunication shelters in India, especially, are run off of diesel fuel.
Right.
So they're running massive generators to just help with people's cell phone connections.
Yep.
So
and then also in the remote environment, like you guys are in, like you technically have to go fill those up.
Yeah,
it's a bit of a challenge. So as we're running out of time here, give us what I heard we want to work with a licensing play and some different stuff like that going forward. Like, I mean, what are some of the things that you need and that you want to see happen with your company going forward? Like, what's going to really light the fuse on your non-fuel combustion model here?
So part of what has been my evolution as an entrepreneur, this is third venture, is understanding the power of networks and how best to engage with those networks in a meaningful way on both sides. And
talking people networks or actual like IT and stuff like that?
Yes.
People networks.
People?
Yes. The first venture, totally on my own, not even outside investors. It was all self-funded and debt-funded. Second venture, had some angel investors who were just monetary only, not really much in the way of connections and Rolodexes that were available. And in the middle of the second venture, I was also a pipeline fellow, and that kind of opened my eyes to the fact that there are a lot of advantages to contributing to an ecosystem and taking full advantage of the connections that come out of that. And so to answer your question directly, what we're really focusing on now is expanding our professional networks and our connections to critical industries and also to the environmental side of the equation as well through things like Patrick had mentioned, the Cleantech Open Accelerator. Next week I'm off to Fresno for the Blue Valley Ventures Accelerator, it's part of the Water, Energy, and Technology Center in California that we're hoping to really gain from in terms of connecting with the California utilities that may have potential rebates for our customers. So a lot of our acceleration, I think, is going to be both contributing to and leveraging the networks that we're working to develop and really expand our potential source of customers and just the people who connect us to those customers. And then finally, making sure that we've got the right product in the right form before we really expand production dramatically, which is kind of why we're focusing on 10 pilots right out of the gate. We want to see what breaks, to your point earlier, Matt.
Yeah.
Understand what needs to be corrected before we have 10,000 of these out in the field and have 10,000 headaches instead of 10. So we're going slow to go fast.
You can sell parts. That's part of your business.
Exactly.
What about you, Patrick? What would you like to add on to that? Like,
well, I think it's all hands on deck. So we're also participating in the small business connection with the federal government. So we think this has military applications in addition to helping the people in the field not carry as much fuel around. Those are typically a large target as people are deploying fuel to forward operations. So we think that by having an off-grid solution would save lives too. So we're making connections with our local SBDC as well as again in California, starting there to then come back and bring this product that is currently 100% made in Kansas. Now we're deploying it across the country.
Do you guys, does the state, are you involved in any of the state of Kansas's programs? Like, that's something I've talked to people about quite a bit. Like, we have angel investor credits and just different stuff. I was recently at a luncheon with the new governor, Laura Kelly, and she was talking about, is the state of Kansas doing stuff to help you guys support any of this?
Totally. And yeah, we've been fortunate enough that many of our investors have taken advantage of Kansas Angel Investor Tax Credits.
Sure, that's good to hear.
Yeah, as a pre-revenue company that's got kind of a brand new technology that's still in development, it's a tough sell to investors. And so the Kansas Angel Investor Tax Credits have been helpful in mitigating some of the risk. There's a lot of value to all of the effort that went into early ecosystems through the pipeline program. Again, originally started in the state of Kansas through KTEC. It's been a great business environment for us.
And our elected representatives are really good too. We were fortunate to meet with representatives from Jerry Moran's office, who's been very forward thinking about both helping our military as well as making our government more efficient.
That's a challenge.
Good luck with that.
Government and efficiency in the same sentence is a challenge. So as we round out this episode, Matt, what's something you need to invent still?
Oh man, I don't know.
A podcast partner.
Well, we're working on the Mapbot.
Yeah.
Yeah, is that?
That's what we need to finish.
Should we team up?
Yeah.
Okay, so you'll be.
I cloned myself already, but he's only 10.
Yeah, I know.
And dog ears.
I cloned myself too, and my wife wouldn't let me name her Payback. So yeah. Well, anyways, guys, thanks for coming in.
Thank you.
And if you get a chance out there in Startup Hustle Nation, go to coldfromheat.com. And sorry for getting the web address wrong earlier. I was at your site and checking it out. There is a little more demonstrative material there that shows and demonstrates some of this stuff. If you get it, also while you're on the internet, go to fullscale.io, check out what Matt and I do. Once again, today's episode is available on our YouTube channel. You can find us on the gram at Startup Hustle Podcast. Some of our other partner companies, Stackify.com and GigaBook.com. More importantly, make sure that you like, review, and subscribe to the Startup Hustle Podcast. See y'all next time.